Hi everyone. This video will discuss mechanical transmissions. In many drive systems there's no direct coupling between motor and load, so-called direct drive, but these systems have a transmission in between. This video discusses the impact of a transmission on both torque and the speed of the motor and the load. Let's start off with this picture. And in this picture we have an electric motor over here and we have the mechanical load over there. And often we see a mismatch between the required motor torque and the required load torque over here. And the purpose of the transmission is to match that motor torque to the load torque over here. And we do that by this mechanical transmission, which transforms this motor torque to a higher torque at the end of the transmission, which equals the required load torque. That is the purpose of that transmission. Can also say that the higher load torque is transformed to a lower torque for the motor at this point. So it transforms a higher load torque to a lower required motor torque. Well, when we have a lossless transmission, we can say that the power at the motor side, P motor, which equals the motor torque times the motor angular speed, has to be the same as the load power over here, which equals T load, so the load torque times the angular speed of the load over here. And that means that when we transform the lower motor torque to a higher torque over here, that the angular speed of the motor has to be transformed to the load side with the same factor, but only it has to be a lower load speed over here in order to make P motor equal to P load. So it transforms, the mechanical transmission transforms both torque and the angular speed from the motor side to the load side and vice versa. Well, there are kind of different transmissions, and the rotary to rotary transmission is very often used. And very often we have a gear transmission, what we can see for instance in this picture, or we have a belt transmission, what we see over here. Another transmission is the rotating to translating transmission, in which we have, for instance, a rotating motor over here, which transforms that rotating movement to a translating movement of the mass m over here. And that is, for instance, a spindle drive. Another rotating to translating transmission is this belt drive, this conveyor, with which transforms this rotating movement towards a translating movement over here. We see it also in carriage drives and in scanning drives, but also the wheels of a vehicle transform the rotating speed to a translating speed, of course. Well, some examples of rotating to translating transformer, so to say, is for instance this linear stepper motor, which transforms that rotating speed from the stepper motor to a linear or translating speed of the spindle over here. We see that also in industrial printing systems. Another example in industrial printing system is, for instance, the carriage drive, in which we have a rotating motor over here, and that motor that rotating speed and torque of that motor is transformed by a long belt over here to a translating movement over here, and towards that belt, this carriage has been attached, and on that carriage there are printhead situated. I'm sorry for that. So the rotating movement over here is transformed to a translating speed of the printheads over here. All right, then a couple of parameters which are very important when we translate linear motion systems to rotary motion systems and vice versa. In a linear motion system, we talk about force in Newton, and a rotary motion system, we talk about torque in Newton meter. Displacements in a linear system in meters become angular rotations in radians, and velocity in meter per second become angular velocity omega and radians per second. The mass in kilograms becomes an inertia, J, in kilogram meter squared, and an acceleration and meter per second squared becomes an angular acceleration in radians per second squared. And of course, the power in a linear system is F, the force, times V, the speed, and in a rotating system, the power is equal to T, the torque, times omega, the angular velocity. Well, when the speed of this part of the presentation went too fast, please look to the appropriate video in this channel. Now let's consider this picture. And we have a motor over here, a rotating motor, and we have a load system over here. And the rotating part, the motor part, has a torque over here, T motor, and it has an angular velocity, omega motor, over here. And at the load side, we have the load torque over here, and we have the load speed over here. And in this system, we can say that at this point within the transmission, this is the transmission in between, we can say that here at this point in the transmission, that force F1 has to be equal to the force F2 over here. So F1 related to this part of the transmission, F2 is related to that part of the transmission. So F1 has to be equal to F2. So when that is the case, we can say, well, T load is the torque over here is equal to F2 times the radians R2. So T load is F2 times R2. We can also define T motor, which equals the transformed load torque over here. So T motor is equal to F1 times R1 over here. So when we divide T motor by T load, so T motor, this expression, by T load, that expression, we get F1 times R1 divided by F2 times R2. But we have seen that F1 has to be the same as F2, so F1 equals F2, so we get T motor divided by T load. This expression is equal to R1 over R2. And that is what we call the ROVB, the transmission ratio. And OVB is the abbreviation of the Dutch word overbringing, the Dutch word for transmission. So the transmission ratio is defined as R1 over R2. And in most of the cases, that transmission ratio is smaller than 1 because we want to have a lower load torque at the motor side or a higher torque at the load side. So the transmission ratio defined by R1 over R2 has to be lower than 1. From this transmission, we can also say that caused by this circumference here and the circumference there, that V1 equals V2. So V1 is equal to omega motor times R1, omega motor times R1. So it equals V2, so it has to be equal to omega load times R2. So the angular speed over here times R2. So when that is the case, we can say that omega load divided by omega motor is also equal to R1 over R2, which is defined as the transmission ratio. So that is important, and we consider in this case the stationary operation, but this is important for the definition of a transmission ratio. Well, let's put it all together and let's look to this picture over here, in which we have a lossless transmission in between the motor and the load. And remember, the motor delivers motor torque and an angular motor speed, and the load requires a load torque and a load angular speed over here. And that transmission transforms the motor torque to a higher torque at the load side, and that is written by T star motor. So it's denoted by a star over here. And that transformed motor torque, which is higher than the torque of the motor directly over here, has to be equal to the load torque. We can also say that the load torque over here is transformed to a lower load torque over here. So this is the transformed load torque denoted by the star over here. And in that case, the motor torque equals that transformed load torque. So we have seen in a lossless transmission that due to that transmission ratio, also the speed at the motor side and at the load side are not the same. So the motor angular speed over here is transformed to a lower transformed motor speed over here, omega star motor, so indicated by the star over here, so that um, omega motor star has to be equal to omega load. You can also say that the omega load over here is transformed by this transmission to a higher angular speed over here, omega load star, which has to be equal to omega load. That is written over here. So when we know that, we can say the torque of the motor is equal to the transmission ratio times T load. So the required motor torque is the load torque multiplied by the transmission ratio, which is by definition smaller than 1. So we see that the required motor torque in this case by means of that transmission is lower than the load torque. That was the purpose of that transmission. And we also see that the motor speed is equal to the load speed, load angular speed, divided by the transmission ratio. We can also put it the other way around. The load torque is equal to the motor torque divided by the transmission ratio. So we want to have a higher load torque. So the smaller motor torque has to be divided by the transmission ratio, which is smaller than 1 over here. So we get a higher transformed motor torque over here. So the load torque equals the motor torque divided by R over B, the transmission ratio. And again, we can say that the angular speed of the load over here is equal to the motor speed multiplied by the transmission ratio, which was smaller than 1. All right, so again, a smaller motor torque has been transformed to a higher torque over here, and a higher load torque has to be transformed to a lower motor torque over here. And as a result, the motor speed is transformed to a lower speed of the load, or we can say the load speed over here is transformed to a higher motor speed over there. That was in case of a lossless transmission. But in practice, we often do not have a lossless transmission, but we have an efficiency in the motor. Or we can say there are losses in that transmission. So we have to take an efficiency of that transmission into account. Remember, this is the definition of our transmission ratio, which is omega load divided by omega motor, which is smaller than 1. When this is the case, and I'm going to calculate it for a dynamic system, so I also take acceleration torque into account, we can say that the motor torque equals the combination of the load torque and the acceleration torque multiplied by the transmission ratio. So in order to get a lower motor torque over here, but because we have losses, we have to divide it by the efficiency of the transmission over here. So in that case, the motor torque becomes somewhat higher because it also has to overcome the losses in the transmission. So again, the motor torque is the combined torque at the load side, so the load torque and the acceleration torque, multiplied with the transmission ratio and divided by the efficiency. And when you work that out, you can see that you get T motor equals T star load plus the acceleration load, and T load star load is the transformed load torque, and T star acceleration is the transformed acceleration torque. What is important is that the efficiency only has impact on the torque, so not on the angular speed, only on the torque. So in a static situation, we can say the motor torque equals the transformed load torque, which is the load torque multiplied by the transmission ratio and divided by that efficiency again. So again, the efficiency only has impact on the motor torque, not on the speed. So it also has impact in the same way on the motor power, because as you remember, the mechanical power equals the torque times the speed, the angular speed. So the efficiency has impact on the torque, so it has also impact on the mechanical power and not on the angular speed. Well, that's all. Thank you for watching, and I see you next time.